Start recording now. Okay, so we're starting to record. This is the open hour on Tuesday, the 17th at 4 to 5. So the question was about carbon dioxide and how the polar vectors cancel for carbon dioxide, why carbon dioxide is a non-polar molecule. And so I was just saying, so here's the model here. And we can see, like, well, the way we want to think of a molecule being polar or not is if one side of the molecule has more electron density than another side of the molecule, like taking into account the whole molecule itself. So when we look at carbon dioxide, right, the way that we drew it on the paper was it's linear, right? So we know that there's one vector going that way toward the oxygen, right? And then another vector going this way toward this oxygen, right? So two vectors. So overall, is there one side of the molecule that has more electron density than the other side?
I think that's where I get confused, is the electron density and stuff. And
Yeah, picture it like this. I'll draw it on the screen, on the board. So here's carbon dioxide. Right? And so we can draw the dipole vectors. Each going toward oxygen because, again, oxygen is more electronegative than carbon. Right? And now that means then on this side of the molecule, there's more electron density, right, toward this oxygen. So there's a partial negative charge on that side of the molecule. But there's also a partial negative charge on this side of the molecule.
Okay.
So overall, there's no like side of the molecule that has more electron density than the other side of the molecule.
Because it's equal on both sides?
Yeah, because it's equal on both sides.
Okay. That makes more sense.
Right?
Yeah.
So, like, similarly, right? So it's equal and opposite. So there, yeah. So like that's kind of like so thinking of it this way is the more like way that can explain why when we say the polar vectors cancel, that it's nonpolar.
Okay.
Like this is why when the polar vectors cancel, it's nonpolar, because there's no one side or other that has more electron density.
Okay. Okay. That makes more sense.
Yeah.
Yeah, because I don't think I was getting it before with the electron density. So I think that's what was the misconnection with it was. Because I understood that the oxygens have more of electronegativity than carbon, but then I didn't know that missing piece. So I think that makes a lot more sense.
Yeah, the electronegativity is connected to how much electron density. And let me show you some images. So here is, I'm going to show you like carbon dioxide, which is nonpolar. I'll show you the image here. Well, let me share my screen. Little baby. So one sec. So carbon dioxide, where are you? whoever's eating, I can tell you're enjoying your meal. But just FYI, we can tell that you're enjoying your meal. Okay, so here's the one I'm gonna show you. Okay, sorry for that. Thank you for being patient. Open up, thank you.
No
Carbon
problem.
dioxide. So here's the image of carbon dioxide. This is the electrostatic potential diagram showing the electron density for carbon dioxide. And we notice, right, that even though there's more electron density on this side, right, there's also the same electron density on this side. Red shows more electron density, so more electronegative, like I've been showing in the red for partially negative, right?
Mm-hmm.
So yeah, so like overall, right, even though there's more electron density on one side, there's also on the other side, and therefore that symmetry like cancels out any like, therefore there's no one side of the molecule that has more electron density than the other. Therefore it's a non-polar molecule, because in order for a molecule to be polar, there has to be like a partially positive end and a partially negative end, just like poles on a magnet, or you know, negative and positive on a battery, or the poles of the earth.
Mm-hmm.
You know, it'd be like if this were the earth, if this were like this spherical earth,
Mm-hmm.
earth would not have a positive north and a south pole if both were south,
Okay.
right? Like if this were, you know, one pole of the earth, it wouldn't be a pole, because they would both be the same.
Okay.
Right? Like this is a negative, partially negative side, also partially negative. It'd be like if the earth didn't have poles, if they were both north or both south or something.
Okay.
Right?
And then for the worksheet that we worked on today in lecture, I got a little lost on how to tell which like bond it would be, or because I think I was getting confused on how to tell if it's a dipole force or the London dispersion.
Dipole or London, yeah.
Yeah.
Yeah. So dipole is so dipole forces are for polar molecules only.
Okay.
And so when do you see where it says polar molecules?
Yeah.
Polar covalent molecules, right down there.
Yeah.
So polar covalent molecules, those are the ones that have that purple permanent dipole arrow.
Okay.
Which we were showing on the chart before this too.
Oh, okay.
And with that permanent dipole arrow, I could have also, see how I pointed where I wrote permanent, and I pointed to the blue, I pointed to the like the blue part, but really like that's permanent, but also the purple dipole arrow is what we're using to show that it's a permanent dipole. So both of those things we're using to show that it's a permanent dipole.
Okay.
And so yeah, whenever you can do that, whenever it's a polar molecule, then the attraction between those molecules is stronger. And we call it dipole because dipole means two poles.
Okay.
Right? So like whenever there's two poles on one molecule, it can attract to another molecule with two poles.
Okay.
Dipole, positive, negative.
So on the chart, the one that we've been working on for a couple of weeks, would an example be would be water? Would that be one with the purple arrow?
Yeah. Water is a polar molecule.
Mm-hmm.
This one here.
Yeah.
Yep. Water right up top there is a polar molecule. And so, yeah, due to water shape, and you can see right above it on the board.
Yeah.
Right?
I didn't even look at the board.
Yeah. Due to water's shape, due to water's shape, there is, remember that, you know how I also showed you the electrostatic potential diagram of water today?
Yeah.
During lecture, we're like, the oxygen end of that molecule has more electron density.
Okay.
So that side of the molecule does have more electron density because it's not symmetrically canceling out. So water is polar.
Okay. That makes more sense.
And then we did draw that one right here, right? For the intermolecular forces, we showed water having dipole interactions where there's a strong connection, right? A strong attraction between the permanently partially negative end of one water to the permanently partially positive end of the other water.
Okay. And then in lecture you also said, so you said something about if you put London dispersion you would get 1 point because all molecules are?
Exactly.
Okay.
Yeah. All molecules have their electrons in constant motion. And so for all molecules and atoms, so even just like, noble gases, for instance, which are just atoms, they're not diatomic molecules or anything, they're just atoms. So like a helium atom will, display, will display London dispersion forces with another helium atom. Yeah. Yep. Yeah. Yeah. And so, yeah. And here, so let's, do you mind? Okay. So I have some other questions. So yeah. So everyone, you'll always get a point on listing intermolecular forces for molecules if you write London dispersion, because they all have electrons that are constantly moving, which would make a temporary dipole. It's not a true dipole, but it's a temporary one, which would attract to another one.
Okay.
Okay, Jamie, you have one question. Oh, it's private, but do you mind if I say it out loud for everyone? Sorry, I guess I shouldn't have said Jamie, but there's a question from an anonymous user that they want to know, let's see, the polarity of atoms is done mathematically, where as the polarity of the molecules depends on the shape, right? That's true. I'd say like it's all connected, but you're right. The polarity of the bonds, I think, is what you mean. Not so much the polarity of the atom, but you're thinking the electronegativity of the atoms, right? Jamie, the electronegativity of the atoms, right? And therefore the polarity of the bond, yeah, is done with this chart here. Right? So the polarity of the bond, and then the polarity of the molecule depends on the shape. Exactly. Okay. You can figure out the speaker, that's okay. Does that make sense? So yeah, like there's two, so there's like, but then it all comes together, right? Like, I'd say like the most important is knowing whether the molecule is polar, but that comes from knowing whether the bonds are polar and the shape, right? So you're kind of like starting out with the polar bonds, if they're polar or not, and the shape of the molecule to tell the polarity of the whole molecule. Is that okay? Okay, you're welcome. Who else? What other questions do you have?
Elizabeth,
Yes.
for next week's lab, Kelsey and I were going over it in the library before they decided to close it all down. And we had a question on the shape of the bent 109 for the second page.
Uh-huh.
For the OPOPO
Yeah.
molecule. The molecular geometry of the second compound in that, in the 3D model, it says it's a bent 109, but it's a bent 120.
Where does it say that?
Well, see, hold on. On mine, doesn't that look like a bent 120?
Show me your video.
How do I do
Okay,
that?
I'm looking now, sorry.
Oh, okay, there.
You're right, that phosphorus is a bent 120.
The first one, and so is the second one, right?
Both phosphoruses are bent 120.
So it shouldn't be bent 109 for the second one.
Both phosphoruses are the same, right?
Yeah.
But then it's not asking about the oxygen on the end, is it? Which oxygen is it asking about?
Oh, for the two centers. So it's asking about the oxygen that's attached to the first phosphorus.
The one in the middle. It's not
Yeah.
asking about the oxygen on the end. Yeah, and don't worry, because we're gonna go over that one during lab. So everyone, if you're not in lab yet this week, when we meet, you don't have to have this worksheet done before you get to lab. It's just, it's good that you're working on it now. Why not? But we'll be going over things.
You got nothing better to do.
Yeah, we thought that I thought that it was due before. I got confused. And so Natalie and I were working on it, but then today in lab and last night when I got your email,
Oh yeah.
I figured out that we weren't supposed to do it. I just got confused. So Natalie and I just decided to work on it.
Thank you. No, that's great. No, nothing wrong with that at all. So, but we'll be going over that one because it's a good one. And yeah, we'll be going over that one. Good. What other questions does everyone have? You can either tune in with your video, audio, or write a question in the chat. And I'm recording, right? I'm recording? Yeah, I'm recording. Okay. My internet connection isn't like amazing here, so.
Oh no, I live up in Boulder Creek, so mine is really bad. My internet connection is super bad.
Yeah, I know. It's everyone too. And then I just want to remind everyone too, like I know you probably got my announcements, but there's all kinds of like free Wi-Fi availability for people during this time. So free and low cost. You can check that out.
And Elizabeth, just because I didn't know if you got my email about for my accommodation time for extending the time on the quiz.
Did you reply? So I don't remember.
I got an email back from you saying to reply to the original, and I did do that. But again, my connection's really bad, so I couldn't tell if you got it or not.
Okay, yeah, I don't think I got it, but let me write it down because I have another person for your class also.
Yeah, if it was online is really difficult for me to understand. So that's why I usually use my time on for online quizzes because it's just easier.
You do what?
That's why I use my my accommodation time whenever I have online quizzes because it's just easier that way.
Oh, definitely. No, of course. You should use it every time. That's fine. No problem. So let me write it down. What else, everyone? I'm so glad to see so many people here. We don't normally have this many in the 4 o'clock, so yay. So this is actually a mixture, so I invited my 30A students too. So this is Chem 30A and Chem 3, so any questions, you're all like in the same, you know, pretty much the same stuff. So anyone, when you have questions, let me know.
I was in the lab earlier for a short amount of time. And I was just wondering, are we allowed to join labs if we're not in that lab and then review it like during our lab time?
So you can join, but I would ask that you don't like necessarily participate. Like you can join to have that practice.
Yeah.
But I'd rather keep the time for the students in that lab, but then you do have to come to your lab time.
Cool.
Is that okay?
I could do that.
Okay. Whatever you want to do. Yeah, if you have the extra time to pop in, that's fine.
What did your 115 group go over for open hours?
Say it again.
What did your 115 open hours go over?
Same idea. We went over all of the like shape stuff. I mean the polarity stuff. We talked about they wanted to know the difference between electron geometry and molecular geometry. So we were going over that. And so up on the board, what I'm attempting to show people is the difference between polar vectors not canceling and polar vectors canceling. When we say that, what we're really saying is like, if the polar vectors cancel, then there's no one side, no one part of the overall molecule that has more electron density than another part, right? Like over here, they're canceling, which means that there's electron density here and here and here, but that's symmetrical, and so they're not, there's no overall portion of the molecule that has more electron density, whereas for water, there is, right? Whereas for water, these aren't canceling, so there's this side of the molecule that is has more electron density, so that is what we call polar, meaning there's partial negative up here. So electron density means partial negative charge, more electron, I don't want to say more electrons, but more, it means more probability that the electrons will be closer to that atom, making it a polar molecule because there's one side that's more electron density than the other side of the molecule.
Okay.
What about ammonia? Everybody, can you tell me if you want to participate if ammonia has polar bonds? Does ammonia have polar bonds? Ammonia is NH3. You can chat.
I think it is polar.
And where are you looking first?
Sure.
Right, where are you going to look? So this is part of the cognitive routine that we want to
Wouldn't it be polar?
facilitate. So if I ask if you want like to draw the dipole arrows on any polar bonds, where do you want to look first?
The way the arrows go, right?
Don't we want to look at our
Right.
electric?
The electronegativity chart, exactly.
I have this.
And I want to let everyone know we're going to run out of time in 10 minutes, but we can just click the link again, everyone. So unfortunately, we haven't been able to upgrade. No one's answering us because Zoom is so like bogged down by all of the new requests that like we should be getting an account where we don't have to stop every 40 minutes, but we aren't. So in 10 minutes, it's going to pause, but then we'll leave the meeting and come back by clicking the same link, okay?
Okay.
Cool.
So how?
Yeah, you look at the electronegativity chart. So the question is, does ammonia, NH3, have polar bonds? And you're looking at the electronegativity chart, right, to see the electronegativity of nitrogen
Which is 3 point.
and hydrogen.
So it is polar.
So it is polar because it's 0.9.
Yeah, the bonds are polar, right?
Yeah.
The bonds are polar. And so we have to, yeah, and so we can draw vectors on the polar bonds, right? I got blurry again. Like this. So are they going to point toward the nitrogen or are they going to point toward the hydrogen?
Towards the nitrogen.
Toward the nitrogen. And there are 3 of them.
So it's polar as well. Okay, cool.
So this is a good one, right? Now the question is the molecule polar? We know we have polar bonds, but is the molecule polar?
Doesn't it cancel out?
That's
So
the question. right? That's the
Would it be
question,
non-polar?
right? So if we look at it like we drew on the board, and we aren't taking into account the lone pair on the nitrogen, it would look like they canceled, right? Because it would look like it was trigonoplanar, like nitrate,
Mm-hmm.
the way we drew it. But this is where shape comes into play. This is why shape is so
Oh,
important,
okay.
right? So is ammonia trigonoplanar?
No.
No.
It's not trigonoplanar like nitrate. Nitrate is in one plane, right? All its atoms. But ammonia, since it has a lone pair,
Is trigonal pyramidal.
is trigonopyramidal. So here's ammonia. So here's ammonia, right? So instead of being flat with all of the atoms in one plane, if I squish it like that, I can make it flat, right?
Mm-hmm.
But in reality, it's in a little tripod shape, a little pyramid shape. So now, is there one side of the molecule that has more electron density than the other? Is there one side of the molecule that has more of a partial negative charge than the other side?
Yes.
Yes.
Which side?
So would it be?
Side closest to us.
So this side?
Mhm.
Well, if I move it this way, would it be this side here toward the hydrogen?
Mm-hmm.
Well, which is more electronegative, hydrogen or nitrogen?
Oh, nitrogen is.
Nitrogen. So is the more electronegative portion of the molecule going to be down here by these hydrogens?
Mm-mm.
Is it going to be on the bottom by the rest of the hydrogens, or is it going to be on top near the nitrogen?
On top near the nitrogen.
Right. And it can be any side, like however you want to hold it. It's just that the nitrogen end of the molecule now, since it's not flat, right? Since it's not flat, but in a pyramid, right? There is more electron density toward the nitrogen.
Okay.
So
it would
overall,
be overall it's polar.
exactly. Overall,
Okay.
this is a polar molecule.
So
So we could draw the like where we're doing right is right now the trigonal pyramidal, right? That's where this comes in. It's in a little pyramid. So right up here, there's partial negative charge. Just like there's partial negative here, here, and here. But this is a nonpolar molecule. This is a nonpolar molecule.
This on the podcast.
Huh? Are you talking to me?
No, so I don't think so.
Nonpolar molecule. Here's a polar molecule. Because we're just showing that there's just one side where there's partial negative. Over here, there's just one side where there's partial negative, right?
Mm-hmm.
And so this is a polar molecule too.
So if there was another H, would that mean it would be non-polar?
If it was at what?
If we added an H to it, would that mean it would be non-polar? Because it's all for N3.
Yeah,
For that,
so let's do that one. Exactly. So like, so ammonium.
Sorry,
right?
yeah.
Ammonium. So we'll open up the chart. That's a great one to think about. Ammonium is right here. We counted well, sorry, it's getting dark, everyone, but when I turn the lights on, it makes a weird glare. So here's ammonium. Oops, where is it? Down here, right? So we kind of started just counting the valence electrons, and then we can draw the Lewis structure. I'm just going to show you what it looks like by using a model here. So nitrogen with not just 3 hydrogens on it, but 4 gives it a +1 charge. And when that happens, so this was trigonal pyramidal for NH3, what is the molecular geometry for NH4+?
That would be tetrahedral.
Tetrahedral. Exactly. So now, do these polar vectors cancel? Now, is there one side of the molecule that has more electron density than another side?
No, I don't. All of
Right.
them are now going at the same spot,
Right.
so they're canceling
Right.
out.
Exactly. So now there's no one side like before, right?
You had
This
one
side of the
whole.
molecule had more electron density.
Okay.
But now this hydrogen is like it's allowing this nitrogen to pull electron density toward itself. So now there's no longer like a side of the molecule with more electron density.
Okay.
Come on. So right. So once you get a tetrahedral shape with all of the atoms the same, it's non-polar.
Okay.
No matter what. No matter if you've got the like fluorines on here, it's still going to cancel out
Okay.
because it's like a symmetrical molecule, and there's not going to be one side of the molecule with more electron density than the other side.
Okay.
How is everyone else doing? Do you want more, or do you have more questions?
Oh, we have less than a minute before the thing's gonna go out.
For sure. So it's okay. So we'll just come back in. Why don't we do that right now? So if I end the meeting, just click the link again, okay? I'll see you back here. So I'm gonna end this meeting and we're gonna start again for part 2 of the open hour real quick.